In this video, I'm going to show you how to use the formal epsilon delta definition of a limit. Now, up until now, we've been using the informal definition of a limit, which is this. If f of x becomes arbitrarily close to a single number L as x approaches c from either side, then the limit of f of x as x approaches c is L. All right, so in other words, basically this is just saying that if L is the limit of the function as x approaches c, then as x gets closer and closer to c, then the value of the function gets closer and closer to L. And we had this limit notation where we could write everything we set up here is captured in this compact little expression, and we would read this: the limit of f of x as x approaches c is L. Now, that seems fairly complicated, but yet I'm calling this the informal definition of a limit. The reason is that as complicated as this is, it's actually sort of vague. What does it mean for f of x to become arbitrarily close to a single number? And what does it mean for x to approach c from either side? So to really nail this down, I need to introduce you to the formal definition of a limit, which is this. This is the epsilon delta definition of a limit. By the way, this symbol right here is the Greek letter epsilon. And this Greek letter right here is the Greek letter delta. So these letters, these variables, are showing up in the epsilon delta definition of a limit, and that's what we're going to explore in this video. I'm going to explain this to you, what does it mean, and then I'm going to show you how to use it. To help us understand, here's the graph of a random function f of x. So if we are saying that the limit of the function as x approaches c is L, right? If the limit is L as x approaches c, then that means as x values get closer and closer to c, then the y values, or the value of the function, get closer and closer to L. So that was our sort of informal definition. Now, what does this epsilon delta definition have to do with what I just said? So before I get into that, let me remind you how absolute value works whenever you have a subtraction. So for example, if I say the absolute value of x minus c, this actually means the distance between x and c. Think about the absolute value of 8 minus 3. This is the distance between 8 and 3. We know that the distance between 8 and 3 is 5. And it wouldn't matter whether I wrote it this way or whether I wrote it this way. The distance between 3 and 8 is still 5. So whenever you see the absolute value around a subtraction, I want you to think distance. So with that in mind, then this first part, all right, this part right here is really just saying if the distance between x and c is less than delta, and then the second part, all right, this part right here is saying then the distance between the function and L is less than epsilon. You might have noticed that I didn't really mention the 0 right here. The 0 is just here to remind us that x is not allowed to equal c. All right, these x values are getting closer and closer to c, but the x value is never allowed to actually be c. We're approaching c, but x can't equal c. So the distance between x and c, of course, has to be greater than 0. So that's all that's saying. Now, looking at the diagram, the delta is right here. And right here. The epsilon is right here and right here. So this part of the epsilon delta definition is saying that if an x value is closer than delta, then the y value will be closer than epsilon. Now, everything I've said so far is really just a description of the second half of the formal definition of a limit. What about the first part? The part that says, for every positive epsilon, there is a positive delta such that all of this stuff is true. What does that part really mean? If the limit of the function as x approaches c is L, then the formal definition of a limit is saying for every epsilon, there is a delta such that this is true. That means that if I give you a number that we'll call epsilon for right now, then you should be able to give me a number, which we will call delta, such that if x is closer to c than delta, then f of x is closer to L than epsilon. Again, just notice that this absolute value inequality means if x is closer to c than delta, because the absolute value part means the distance between x and c. So if the distance between x and c is less than delta, of course that means that x is closer to c than delta. Similarly, this second absolute value inequality means this. And again, the absolute value part means the distance between the function and L. And if the distance between the function and L is less than epsilon, that means the function is closer to L than epsilon. So if you're feeling a little bit lost right now, don't worry. This concept is pretty hard to understand when everything is all variables. This is going to make a lot more sense after we do a few examples. Problem number 1. Given the limit as x approaches 3 of 2x minus 5 is equal to 1, then the formal definition of limit says that for every epsilon, there is a delta such that this is true. Now, please remember that the c is right here. This is the c. So in this case, c is 3. Also understand that, see the f of x right here? This is f of x right here. And the limit is right here. This is the limit. So let's go ahead and put these three things where they belong in this inequality. All right, so instead of c, let's go ahead and put 3. And let's, instead of f of x, let's go ahead and put 2x minus 5. And instead of L, let's go ahead and put 1. All right, So the formal definition of a limit says that if the limit of this function as x approaches 3 is 1, then for every epsilon, there should be a delta such that this is true. For every epsilon, there is a delta. Remember, that means if I give you an epsilon, you should be able to give me a delta that makes all this true. So let's try that. I'm going to give you epsilon. So let's say I give you an epsilon of 0.01. All right, so if I give you an epsilon, you should be able to find delta that makes this true. And that's what I want you to do. The key to finding delta is we need to find something in common between the two inequalities. Since we were given epsilon, let's start with the second inequality and see if we can rewrite it until we get something that is in the first inequality. So we have the absolute value of 2x minus 5, and then we have this minus 1. I'm taking away the parentheses because they're not really doing anything right now, is less than 0.01. Now, simplifying this a little bit, we will have 2x minus 6 is less than 0.01. Now remember, I'm trying to get, if I can get an x minus 3 going, that would be great because I see that in the first inequality, and I want something in common between the two. So what if I factor out the 2? So then I would have the absolute value of 2 times the quantity x minus 3 is less than 0.01. So there's my x minus 3. I'd love it if this were the absolute value of x minus 3. And it turns out there's nothing wrong if I take the 2 outside of the absolute value. That will not change the value of this expression at all. All right, just multiplying by a positive number. It won't change the value regardless of whether it's in front of the absolute value or inside. So this will become 2 times the absolute value of x minus 3 is less than 0.01. So to get this down to a simple x minus 3 like we have in the other inequality, I'm going to go ahead and just divide both sides of the inequality by 2. All right, so if I divide both sides by 2, then I'm going to get, I'm going to try to squeeze it in here, I'm going to get the absolute value of x minus 3 is less than 0.005. Notice that we were looking for a delta so that the absolute value of x minus 3 would be less than delta. And look, that's exactly what we have right here. We have the absolute value of x minus 3 less than a number. That means that this number must be our delta. All right, so now we can just work backwards and show how this works. So we're going to go ahead and just choose delta to equal the 0.005. Now it's going to be really easy to show that our first statement, with this delta, will lead to the second statement. So if we choose delta to be 0.005, then this green inequality becomes this. All right, so if 0 is less than the absolute value of x minus 3, and now we have chosen a delta, so we can go ahead and say which is less than 0.005. Now our job is to show that if we use this delta, then it will lead to this purple inequality. All right, so all we are really going to do is we're going to do the steps that we did here in yellow in reverse. Okay, so it would be easy to multiply both sides of the equation by 2. Instead of dividing by 2, we're going to multiply by 2. So, and you're going to see me use the word implies a lot. So if we have this original statement, this implies that 2 times the absolute value of x minus 3 is less than 0.01. I just multiplied both sides by 2. But this implies that the absolute value of 2x minus 6 is less than 0.01. And factoring out, well, not factoring, but splitting up the 6, this implies that 2x minus 5 minus 1 is less than 0.01. I just took the minus 6 and split it up as minus 5 and minus 1. You can see that these are equivalent. And, oh look, this is what we were shooting for. We had to show that the green statement would lead to the purple statement if we chose the right delta. And we just showed that if we choose delta to be 0.005, then the green statement does in fact lead to the purple statement. So going back to our picture of give and take, the idea is that I gave you an epsilon of 0.01 and you gave me a delta of 0.005 that would make all of this true. Before we move on to the next example, let's look at this problem in the context of a diagram. So we were given a function where the limit as x approaches 3 was equal to 1. That meant that for every epsilon, there should be a delta such that if an x value is closer than delta, then the y value, or the value of the function, should be closer than epsilon. So if I give you an epsilon, you should be able to give me a delta that makes that true. And that's what we did. I gave you an epsilon of 0.01, and you found a delta of 0.005, such that any x value, if the x value is closer to 3 than 0.005, then the y value will be closer to 1 than 0.01. Now, if this is truly the limit, I should be able to do that for any epsilon. Any epsilon I give you, you should be able to give me a delta. Problem number 2. Using the epsilon delta definition of limit, prove that the limit of 3x minus 2 as x approaches 2 equals 4. To do this, we must prove that for every positive epsilon, there is a positive delta such that I went ahead and copied and pasted the formal definition of a limit so that you can compare this to what I am about to write down. So, such that if 0 is less than the absolute value of x minus 2 is less than delta, then three x minus 2, that's f of x, minus L, and that's 4, will be less than epsilon. Again, the key is to start with the epsilon inequality and then try to rewrite it so that you can find something in common with the delta inequality. So I'm just going to go ahead and start working on that. So I've got the 3x minus 2 minus 4. I just took away the parentheses because they're not really doing anything. Notice that on the previous example, we were given a value for epsilon, and then we were finding a delta. This time, we're just going to leave epsilon as a variable and see what happens. So let's keep going. So we're going to have 3x minus 6 is less than epsilon. And we really would like to get the absolute value of x minus 2. So I'm noticing that if we factor out a 3 right now, then that's going to produce the x minus 2. And we can take the 3 outside the absolute value, no problem. It will still be the same. It's less than epsilon. So now we have the x minus 2, the absolute value of x minus 2 in common. But we want to get that absolute value by itself. So I'm going to take the final step of dividing both sides by 3. All right, so in that last step, when I get that absolute value by itself, I have found my delta. All right, so I'm going to have the absolute value of x minus 2 is less than epsilon divided by 3. So guess what? This is going to be my delta. All right, it's okay that the delta is not a specific number. The delta can be a variable, can be an expression written in terms of epsilon. And in fact, that's the only way to prove it for all values of epsilon at the same time. So the way we finish off the problem is really to repeat the steps that we just did in reverse in order to show that the delta inequality will lead to the epsilon inequality if we choose the right delta. In this case, we decided that we're going to choose delta to be equal to epsilon over 3. All right, so we're not finished. We have to work backwards and show that using this delta, the delta inequality will lead to the epsilon inequality. So let's substitute this expression, epsilon over 3, in for delta and show that it leads to the epsilon inequality. All right, so we're going to have 0 is less than the absolute value of x minus 2, which is less than epsilon over 3. All right, that's where we begin. So let's work our way back to this. So this is going to imply, and you're going to see me write this word implies over and over again. So implies, all right, it just means that this leads to the following. You'll notice that I'm just multiplying both sides of the inequality by 3 to get me back to epsilon. So if I multiply by 3, this implies that 3 times the absolute value of x minus 2 is less than epsilon. Multiplying by 3 cancels out this 3. And this implies that the absolute value of 3x minus 6 is less than epsilon. It's okay that I multiply inside the absolute value. This is a positive number, so it will not change the value regardless of whether I'm multiplying outside or inside the absolute value. Now, I can see how similar this is to my epsilon inequality. I've got the epsilon, I've got the 3x, I've just got this minus 6 where I need a negative 2 and a negative 4. So let's just split that up. So one more time, this implies that the absolute value of 3x minus 2 minus 4 is less than epsilon, because these are the same. So that's it. We have proven that this is in fact the limit of the function, because we have shown that for every epsilon there is a delta, such that if the delta inequality is true, then the epsilon inequality is true. Specifically, all we have to do is choose delta to be epsilon divided by 3, and the delta inequality will imply the epsilon inequality. One leads to the other as long as we choose delta to be epsilon over 3, and that proves it. Let's take one more look at our give and take picture. If L is the limit of the function as x approaches c, that means that for every epsilon, there is a delta that makes all of this true. In other words, if I give you an epsilon, you should be able to give me a delta. And for the problem that we just looked at, if I give you any epsilon, you're going to give me delta, but delta is always going to be epsilon divided by 3. So for example, let's say I gave you an epsilon of 0.12. Then you would give me a delta of 0.12 divided by 3, which is 0.04. So in the same way, using this little formula, we can see that for any epsilon, there will be a delta that makes all of this true. By the way, I didn't draw these pictures. My daughter Maya drew these pictures. These were my pictures. Go ahead, laugh it up.